continue with the physics of the rotating machines. And last class, if you remember, we told you about some important aspects of the rotating machines. One thing is there must be a clear distinction between electrical angle and mechanical angle. And we saw that electrical angle last time we did that P by 2 into mechanical angle. And also we defined what do we mean by a full pitched coil. A full pitched coil is the one whose coil span is 180 degree electrical, whose coil span is 180 degree electrical. Now today what we will do is this: suppose a coil in a machine carries some direct current. What will be the field distribution in the air gap of the machine? So to do that, what we will assume that suppose we will take a very simple case. Suppose there is on the stator of the machine there are two slots. There are two slots like this. Suppose there are two slots like this on the machine. On the rotor of the machine, we started like this. So this is suppose the stator. So this is stator, where there are no slots. It is only iron. On the rotor, there are two slots diametrically opposite, indicating that it will be a two-pole machine. And there is a coil which goes perpendicular to the plane of the paper. At the end they are joined, and in the forward direction I have got two free terminals, as I told you. Now this coil, suppose it is energized by a direct current. So this coil, whenever it will carry current, will produce field along the horizontal direction. Is not? Whenever it carries current like this, it will produce field along this direction. So representation of this coil could be made, in this fashion. This is the coil, two free terminals, and if this coil carries current, it produces field along the horizontal direction, because the magnetic axis of the coil is perpendicular to the plane of the coil. That is okay. Now suppose this current, it will carry, I will say that this side carries cross current and this side carries dot current. Okay, suppose this terminal we call of the coil 1 and this is 2. So by giving supply, say from a battery, I can make the coil carry current in this direction. This side is 1, coil side 1, this is coil side 2. So it will carry current in this direction, and the field produced will be along this line. So this is the symbolic representation of the coil, and it will carry current in this direction. Now next what we do, our problem is to find out what will be the B distribution along the air gap of the machine. Stator does not carry any winding, only it is having iron. So stator is iron with no slots, and rotor is also iron with a pair of slots. Now this diagram, what you do, you cut and make a developed diagram. So it will look like this one. On the stator, it will be a line like this. This will be the stator. And on the rotor, there will be an air gap, and on the rotor there are two slots like this. These are iron. And here is your coil 1, coil side 1, and this is coil side 2. and this is the air gap. Air gap of the machine. And as I told you, suppose we pass some direct current in this coil 1 and 2. Then what will be the, how to calculate the field distribution along the air gap? The calculation of field is rather simple. Only thing we will assume first that let the permeability of iron is very large compared to air. So we will apply Ampere's circuital law to find out the field distribution. For example, the lines of forces here due to this conductor, it will be like this. This will be dot coming. So there will be several lines of forces going like this and completing their paths. Suppose I want to find out what is the field at this point. So I consider a lines of force, closed lines of force circuit, the direction of which I find out by your right hand rule. That is, you put your thumb along the direction of the current, other fingers will give you the direction of the field. Now suppose H is the field here. Then H into L, you know H integral L is what? Current enclosed. And it is a closed path. Now under this assumption that the permeability iron is very large compared to air, this MMF will be primarily dropped where? Only in the air. That is as if no MMF is required to drive flux through the iron of the machine. Therefore, if this is the value of H for this path, then suppose I start from this one. H into, suppose G is the air gap length. H into G. Whatever is the value of H, I want to calculate. H into G here. Then from this to this, no MMF drop because the reluctance offered by the iron is very small. Reluctance offered is very small. No drop of MMF takes place. And then from this to this, there will be no MMF drop. Then once again from this to this, there will be another H into G. The direction is same, this arrow. And from here to here, no MMF drop is taking place. So this should be equal to the current enclosed, which is in this case, if it is a single turn coil, is I. Now at this stage, I will tell you what is a multi-turn coil. A multi-turn coil, I told last time, I think, that is a coil which is having a several number of turns, having two coil sides, but each side will have then several conductors. For example, a multi-turn coil will look like this way. Last time I drew, if I remember. Suppose you start from this one, go this. A single turn coil, here is the end of the coil. But here in this case, it will now go through the same slot. Several section of conductors will come. So this is a two-turn coil. Therefore, if such a coil are put on these slots, how it will look like in these slots? There will now come two sections of conductor. That is this and another, and this another. Are you getting? So a coil may consist of, which is generally the case, having large number of turns. So suppose if the number of turns is n instead of a single turn coil, then this equation should be equal to Hg plus Hg is equal to into n into I. where n is the number of turns of the coil. N is the number. Therefore, 2Hg will be equal to Ni, or H in the gap here will be Ni by 2G. Remember, this is a DC current, so this field will be produced. Therefore, if I want to plot this value of H along the air gap length, along the length of the periphery of the machine, along the air gap, then what do you notice? Do you think what will be the H value if I have calculated it here? Suppose at this point I have calculated, gone like this. But suppose I have calculated the H value, I want to know what will be this value here at this point. It will be once again same at this point and at this point. Therefore, however, one should note that with respect to this conductor 2, at certain distance, the value of H will be same as at this point, symmetrically placed with respect to conductor 2 here. But their directions are opposite. If you assign this to be positive, this should be negatively directed. That is very clear. Now suppose if I plot this MMF wave along the length of the machine, it will be like this. Suppose this is my reference point from which I am measuring the position. That is the slot number 2 here. This is slot number 1. So you will find the MMF will be, distribution of MMF along the air gap will be rectangular in nature. And in these slots there will be a jump. We do not know, it is undefined. But from plus to minus it will be like this. That is, this point, from this to this is this to this. Here all the lines of force will be upwards. And suppose I have assigned positive sign to that. So till the slot number 1 is reached, it will remain constant here. But the moment you cross this central line and comes here, it will become negative. Okay, the MMF direction is from top to bottom. That is, if you assign this is to be north, this should be south. That's all. Mathematically we represent like this. So this will be the MMF distribution of a coil, and this one will be repeating itself because it is a rotating machine. So this will be like this it will go. I mean, if you once again come back after 2 pi, means you are coming back here once again. After 0 to 2 pi, you are once again coming back here. So this way it will be represented. What will be the amplitude of this one? The amplitude of this one we have just calculated will be Ni by 2G, where G is the air gap of the machine, N is the number of turns, and I is the current. This is the MMF distribution of a single coil. So on this axis we have plotted H, and this is the angle theta, space angle, which fixes up at what point you want to know H. What will be the B distribution? You simply multiply this curve with mu 0, because in the air gap we have calculated. So this, if you multiply with mu 0, you will get B distribution. Okay. So B distribution becomes rectangular in nature. However, in machines, single coils are not used. Several coils are used and distributed in slots. For example, a typical slots will be like this. Typical stamping of the machine will be like this. There will be several slots here, and these are called teeth in between this iron. Now through this the conductors are placed, as I told you, along the length of the machine is perpendicular to the paper. So and these are called stampings, as I told you. a large number of stampings are stacked together, aligned in such a way that slots are slots all along the length of the machine. There is no offset, so that, and you put your conductors like this in one slot, and it goes at the back, it comes, and through another slot the return of that coil side comes out. Which slot it will come out? Of course, that it will depend upon the electrical angle, etc. But anyway, and there will be large, say, this space will be occupied by a large number of turns. So a single turn, a single coil may occupy these two positions, and they may have large number of turns. Okay, this is a stator stamping or rotor? This is stator, of course, because this inner side is slotted. Okay. But anyway, this is Ni by 2G. Now, what I want to tell you, suppose you have a machine, the same machine, but with say 2 or 3 number of slots. Suppose on the stator there is no slots like this. This is the rotor. Suppose you have a slot here and here, here and here, and there and there. Suppose this is 1, 2, this coil 1, 2, this is 3, 4, this is 5, 6. So there are coils, 3 coils now, and each one may be multi-turn coil like this. 3 is another coil, 3, 4, multi-turn. 5 is another multi-turn coil, 5, 6. And each coil will have their 2 free terminals available to you, like the coil 1, 2, 3, 4, 5, 6. So these 3 coils, you connect them in series. See, 1, 2 is the 2 free ends of one coil. Another coil is 3, 4. Another coil is 5, 6. Suppose all these things we connect them in series and pass DC current, pass DC current here, such that they are connected in such a fashion that this side, suppose this side, the conductors carry cross current, and this side they carry dot current. Okay, suppose these 3 coils are distributed in space and they are joined in series and excited from DC supply, then what will be the nature of the field in the air gap? How will you find out the nature of the field? In the light of the knowledge we have got for a single coil. So for one coil it is like this. I will tell you the idea. For one coil it is like this, 1, 2. 3, 4 will be also like rectangular, but it will be shifted by some angle. Is it not? So for example, if you just cut it and develop, it looks like this on the rotor. This is one slot, this is another slot, and this is another slot. Then once again after some time, this return of these 3 comes. Suppose this I call 1 carrying cross current, and it will have 2 here. Then you have, first 4 I should draw. Whatever way, these 3 coils comes here, and this will be dot. This will be dot, this will be dot, like this. Let us not put, this, and this. Now, so far as this pair is concerned, what will be the nature of the field? The nature of the field is, in this case, it is cross, so you can find out. It will be like this for this slot. Next slot will be similar. This and this will produce similar MMF, but it will be shifted by this one, rectangular. Then what you should do? You should add them point by point. At a particular position, I know in space what is the net resultant field. I will add these 3. So what kind of MMF waveform you will get now? You will get a stepped waveform. That is, this you can do. Is that clear what I am trying to tell? This MMF you find out. For this one also you find out its resultant MMF. For example, here at this position, suppose this is the stator. What will be the field? 3 Ni by 2. Because this plus second one plus third one. So the MMF distribution of such a system of 3 coils will be stepped in nature. Ni by 2, Ni by 2. Like this, it will come. This I tell you to do on a graph paper. Assume 3 coils equispaced and add them up. See, it will come like this. Therefore, the point I want to tell that when you use a single coil, it is rectangular in nature. Otherwise, if there are several coils which are distributed and connected in series, the MMF or age distribution will be stepped in nature. Age distribution is stepped in nature. Now, why it is done, you can understand. You see, we have to produce somehow a sinusoidal distribution of B, because induced voltage, we have seen earlier, it becomes the whatever space distribution of B is there, that will be your EMF, BLV. LV are constant. B in whichever way it is distributed. The EMF induced in conductors will be also like that. If you want to generate AC voltage, you must see your B distribution along the air gap of the machine is more like sinusoidal. If you use a single coil, it is far from sinusoid. It is a rectangular one. In such situation, if you want to find out what will be the voltage generated, what is done is this rectangular waveform is Fourier analyzed, and you will be having a strong fundamental and several harmonics. So there will be induced voltage because of fundamental and also because of several harmonics. It will not be a pure sine wave. We will see how the induced voltage because of different harmonics can be eliminated at later stage by not using a full pitched coil. I told you it is generally full pitched coil we should get. It can be shown that by not using a full pitched coil, you can eliminate some of those harmonics here. Anyway, this is something worst, a single coil rectangular distribution. But this one is far better. That is, this one it looks more like a sinusoid already. If you Fourier analyze it, its fundamental component will be quite strong. There will be, of course, in this case harmonics, several other harmonics. But it is certainly better than this option, instead of using a single coil to produce a flux like that. In fact, we will deal with the fundamental component alone at this stage, and we will see if there are harmonics, how to avoid the effect of harmonics either in the induced voltage or in the calculation of the torques of a machine. So our first assumption will be, we will concentrate our attention, concentrate your attention to the fundamental component, Or we will assume B distribution is sinusoidal in nature. Other way, if you tell that is B distribution, let it be sinusoidal. But I wanted to tell how B distribution can be made closer to sinusoid. So in a single winding, if you excite by direct current, the MMF distribution will be this one. It will also have a fundamental component. So what I am trying to tell, be it a single coil or multi number of coils connected in series, we will first examine what happens to the fundamental component of that. We will deal with the fundamental component. Okay, you tell me, suppose in the first example, that is the simple coil, single coil case, that is this one. This one. If instead of direct current, if I excite the coil by alternating current, this current, this one, instead of DC, if I replace it by some AC source, what do you think the field distribution will react to that? Exactly, it will once again remain rectangular in nature. But amplitude depends upon Ni by 2, is not? Ni by 2 is the amplitude of this one. This I now becomes a function of time. I now becomes a function of time. When I is 0, this will be a flat line. When I is maximum, this will have its maximum amplitude, rectangular shape. When I is negative, the direction of MMFs itself changes. That is, this will remain rectangular in nature, but it will pulsating with time. That is, this MMF waveform, this amplitude is changing, going like this, coming to 0, going to negative. It will do like that if I is time varying. In whichever way I varies, MMF distribution too will vary. Now, if I only concentrate on fundamental, that means if a single coil is there, suppose a single coil, the MMF distribution is like this, or B distribution, or MMF, H or B or MMF, whatever you call. This distribution is like this, only fundamental component. And this is the space angle. Don't confuse it with time angle. This is space electrical angle, space angle. So if this amplitude will be changing with time as you change current values. It will sometimes like this. At different instant of time, it will be like this. And this MMF, that is when excited, means when coil is excited by AC current. This will be the sort of MMF distribution. And this sort of MMF distribution, or H or B distribution, is called a standing pulsating wave. Standing pulsating field. The wave is standing at one place, but its amplitude is going on changing. So it is called a standing pulsating field. Therefore, a single coil excited by a single phase source will result into a standing pulsating wave all the time. Now I will go to a very basic three-phase coil and show you how the nature of field changes, and that is the beginning of three-phase induction motor. That is very important. You try to understand it. You consider, see, an elementary three-phase coil. Elementary three-phase coil, three-phase winding. Elementary three-phase winding. You suppose consider a stator has got 6 slots, equispaced 6 number of slots. Such that the angle between 2 consecutive slots will be 60 degree. So what you do, you divide this one by this one. This is 120 degree. So each angle is 60 degree, and here is one slot on the stator. Here is another slot. Here is another slot. Here is another slot. So there are 6 number of slots. Each angle is 60 degree. Now what you do? Suppose a 3-phase winding I want to make. So I start with R phase winding. So this slot I allow to, I call it say R1, and its return will be here R2. A single coil. So this is, suppose this coil, let it belong to R phase coil. Tell me where from the Y phase coil will start. Which slot? Third one. That is this, because 120 degree apart. And are we making the windings 2-pole or any other pole? For this one? Certainly 2-pole machine, because once I have chosen the coil span is equal to 180 degree mechanical, 180 degree electrical is always correct, but it is diametrically opposite. It means it will be a 2-pole construction. Why 2-pole? Because whenever R phase, see, any phase will carry current, it will produce only 2 poles, not south or south north, like this. See, a individual coil, how many poles it can produce will decide what will be the number of poles of the machine, as we will see later. But it is certainly a 2-pole configuration we are trying to do, because I have put the return coil side in diametrically opposite slots. So R1, R2. So Y1 will start here. Y1 will be here, return, and its return will be here, there, Y2. And B phase obviously then will start after 120 degree from the start of the Y phase, and this will call B1, B2. Also you can easily show the magnetic axis of R phase is horizontal, and magnetic axis of Y phase is 120 degree apart from this horizontal line. It can easily be shown. Similarly B phase, like that. Now this coil I will just show like this. That is, this is suppose R1, R2. This is Y1, Y2, and this is B1, B2. With respect to their magnetic axis, this can be shown in this fashion, the symbolic diagram, simplified diagram. Now what I will do is this, these three coils, I will join them in series, and not in series, in star, suppose R2, Y2, B2 I will short. And here these 3 terminals I will give a balanced 3-phase supply, a balanced 3-phase supply. Now a balanced 3-phase current will be drawn provided the windings are identical in nature, R phase, Y phase, B phase. That is what it should be. That is, the number of turns in R phase, Y phase and B phase are equal. So they will draw, say, this is IR, this is IY, and this is, say, IB, like this. Okay. Now how to find out the MMF distribution along the air gap of the machine because of all these 3 currents, and which are distributed in a particular fashion like this. What will be the nature of the MMF along the air gap of the machine? And for the time being, you can assume that the rotor is a just iron. We don't take into account whether any rotor current is flowing or not, things like that. It is iron. Rotor is iron, so that lines of force will be nicely completing their paths. Now, the currents are balanced three-phase current. So I can assume that IR is equal to sum I max sin omega t. IB is equal to I max sin of omega t minus of 120 degree. I mean IR IY, sorry, IY. And last is IB, RYB, which is same current I max into sin of omega t plus 120 degree. And current direction I have assumed like this, all entering to the one terminals R1, Y1, B1. Now let us take several instants. Suppose you say at omega t equal to 0. Omega t equal to 0. What is the value of IR? IR is 0. What is the, so R phase will not carry any current. This R1, R2 is not carrying any current at omega t equal to 0 at that time. See, I want to find out what is the resultant MMF distribution along the air gap of the machine. So what I will do is, I will consider several instants. Suppose at omega t equal to 0, let us take a photograph how the currents are distributed in the conductors at that instant. Let us freeze that one at omega t equal to 0. So what should cross dot, what should I show in R1, R2? Nothing, because at omega t equal to 0, IR is 0. Now what is IY? Tell me, put omega t equal to 0. How much it is? Sine of minus 120 degree? Minus root 3 by 2 I max. Is it correct? That I leave it to you. Sine. And then IB will be how much? Plus root 3 by 2 I max. Now let us show this current distribution in Y and B phase. R phase is not carrying any current. So Y B phase, let us say, it is IB in this direction and it is positive, means really it is entering through Y1 and leaving Y2. So in Y1 I should put a cross and in Y2 I should put a dot. Now that is B, no? Sorry. B is positive, just wait. B is positive. This is not IR, this is IB, sorry. This is IY. I'm sorry. This is IR, this is IY, this is IB. So IB is positive, means current is entering through B1, that is, this is cross, and this should be dot. And come to Y phase. Y phase, IY is negative. IY is negative, means that current is actually entering through Y2 and leaving through Y1. So current is entering through Y2 and leaving through Y1, that is, this should be dot. So this is cross, this is dot, this is dot, this is dot. Now, what will be the direction of the field? For that I don't do any mathematics. Direction of the resultant direction of the field at that point of time, in which direction it will be directed. Is it horizontal? Is it vertical? See, this is two coils, on this side cross, this side dot. So the situation is like this. Current is going, coming out. So it will be directed downwards in the vertical direction. So the resultant field at omega t equal to 0 will be somewhat like this, downwards. Are you getting? Similarly, you can find out at omega t equal to 30 degree. say at omega t equal to 30 degree, you can find out the distribution of the current and find out how the current distribution, take a snapshot at omega t equal to 30 degree, freeze that, what is the current distribution at that one. And you can do it for several instants of time, omega t equal to 60 degree, omega t equal to 90 degree, like that. And try to get a feeling what is happening to the resultant field distribution along the air gap of the machine. But let us, we can do that, we will do also. But let us do it by somewhat mathematical expression in the light of this whatever we have learned earlier, that a coil, single coil, when it carries some current, it produces a rectangular field, and that rectangular field we will consider only the fundamental component. From that point of view, we can also find out the resultant field distribution. For example, what I want to say, that mathematically, you consider this is your, say, R phase coil, R1, this is Y1 we have calculated, Y1, and this is B1. Suppose I want to find out the field distribution at any angle theta in space. At this point I want to find out the resultant field. For R phase, the distribution of MMF, see MMF by A phase or R phase will be equal to, it will be proportional to number of turns of A phase into IR. And what should I write here? If suppose I take the reference of the maximum value of the MMF produced by A phase as theta equal to 0, then with respect to theta, what should I write? Cos or sin? Cos I should write. Suppose the axis of R phase, I have taken my reference for space angle measurement. So with cos theta it will be varying like this. So what will be Fy? Fy will be n into Iy. But same theta I want to consider. So what should be here? With respect to Y phase, so for cosine minus plus it does not matter, so it can be written as cosine theta minus 120 degree. And for B phase, it will be n Ry B, cosine theta plus 120 degree. This is how the, at any point, space point I have fixed theta. I want to find out what is the contribution here because of R phase, because of Y phase, and because of B phase. And I should add them up to get the resultant. I will do that physically, something with arrow, but this is what I started with. Let me complete this one first. This you have understood or not? See, R phase, there is a coil. It produces MMF distribution, which I have assumed to be sinusoidally distributed. And where from I am measuring theta? From the axis of that R phase, theta. So it will be some n proportional to NIR into cosine theta. This will be cosine theta minus 120, like that. Now let us assume that this IR, IY, IB, just for convenience in mathematical steps, let IR be I max instead of DC current. Suppose it is I max cosine omega t. IY I max cosine omega t minus 120 degree. And IB is I max cosine omega t plus of 120 degree. Cosine I can assume, just it will help me in calculations. That's why I am doing this. So substitute this here. So FR will be some constant here. This n into I max into cosine omega t cosine theta Fy mmf will be same constant 10 I max cosine omega t minus 120 degree into cosine theta minus 120 degree. Theta is space angle and FB is k into n into I max into cosine of omega t plus 120 degree. So the resultant field, F resultant, will be sum of these three. Sum of these three can be calculated this k into n. What is n? N is the number of turns per phase. Into I max you take common. Divide it by 2. Multiply it by 2. So 2 cosine A cosine B. So cosine of A plus B plus cosine of A minus B, the first term. Then plus of cosine of A plus B, that is omega t plus theta minus 240 degree. Plus of cosine of omega t minus theta, the second term. And lastly, plus of cosine of omega A plus B, that is omega t plus theta plus 240 degree. And plus of cosine of omega t minus theta. This will be the resultant field, this F resultant. So, how much it will become? The first column, if you add, this becomes 0. Sinusoidal term 120 degree displaced. So, F resultant will become some 3 kn I max by 2 into cosine omega t minus theta. This will be the resultant. What kind of resultant field it is? Is it standing pulsating wave or is it something else? It is a traveling or rotating field. How? Because at omega t equal to 0, suppose you take a snapshot of this equation, how it will look like with respect to theta? It will be distributed like this. This is space angle, theta. Omega t equal to 0. At omega t equal to 0, what is the equation? Cosine minus theta, it is like this. Is not? See, omega t equal to 30 degree. This will be cosine 30 degree minus theta. Means cosine 30 minus theta minus 30, same thing. So, it will be once again a cosine wave with respect to the first one, omega t equal to 0. It will move by 30 degree. At omega t equal to 60 degree, same distribution but shifted towards right. Therefore, it represents a traveling field moving from left to right, and I will discuss in greater detail. Today I did it slightly faster next class.